Thank you for watching our Process Control Group Project presentation. For this project, we decided to address some issues in art preservation by creating an automated humidity control system. Going into the background of this project, there's the problem that many pieces of artwork require a specific humidity level be kept for their proper preservation. This applies to paintings, artifacts, and old, small sculptures. From this, we gave ourselves the problem statement to create a completely automated humidifier control system. Going into the design of what this might look like. Here on the left is our initial proposed design. This includes a fan-vented case with a piece of artwork on the inside, a humidity sensor which can communicate with an ESP32 microcontroller. The microcontroller can then send a signal to a humidifier through the humidifier controller. The humidifier has access to water reserves, allowing it to introduce water vapor into the case. Then here on the right is our final design, and I'll now show a video of this apparatus functioning. Here is our brief overview of our process control project apparatus, including an enclosure, an example painting, humidity sensor, humidifier, a fan, and ESP32 microcontroller. When this light turns on, the humidifier begins to output. It's hard to see. You can kind of see in the black background, but it's hard to see on camera. But that is being controlled based on what this humidity sensor is sensing. To get to that final design point, we went through a series of steps. First, we modeled the behavior of the system. We performed a few step tests with the humidifier, and from that derived this FOPDT model. Using that, we were able to get several design parameters for our controller. We then were able to create a data-driven model to predict what the behavior of our system might look like in a set point change. Using this information, we were able to design a controller for our system. Our system implements a PID controller. Initially, we just used a PI controller. However, we later found through testing that the derivative term was especially important for the overshoot of the system. Our controller is based on IMC tuning parameters, and we tune these parameters through different set point steps to optimize the overshoot and the rise time of the system. Through this, our controller has the following results. This graph summarizes the results of our system and its controller. It shows the set point jump from 35% humidity to 45% humidity, and the system's attempt to track those set points. On the bottom is what we call the duty of the humidifier, and this blue line shows the humidity inside the enclosure. Important to note is that the 35% humidity, we see a bit of overshoot, and the system tries to adjust to that. Then, at 200 seconds, when the set point steps from 35 to 45, it takes about a minute for the humidity to get to that 45% level. Overall, the system is able to track specific set points very well, and for actual implementation, there would only be one specific set point that you could tune further the parameters to get exactly what you need for the specific piece of art.